This is Unit 6 and we're on page 5. So on the previous page we derived some ideas. So returning to the middle of the derivation, we find a useful formula. Force times time equals delta P. On the left side of the formula, force times time is given a name. Impulse. The formula says that if we exert a net force on an object over a period of time, we will change the object's momentum. The formula here, force times time equals delta P, and in words, force times time is impulse. Impulse equals change in momentum. So if we exert a net force of 80 newtons on an object for 10 seconds, force times time, we have exerted an impulse of 800 newtons times seconds to the object, and have changed its momentum by an amount of 800 kilograms times meters per second. So if you look at these units here, 1 Newton times seconds equals 1 kilograms times meters per second. So looking back up here, force times time, I'm going to label this as impulse. In order to change the momentum of an object by 100 kilograms times meters per second, we could do it in a few different ways. So force times time equals change in momentum. Impulse equals change in momentum. So if we want to change the momentum of an object by 100 kilograms per second, kilogram meters per second, what is the force that we need? So a force exerted over 5 seconds changes the momentum by 100. We need a force of 20 newtons. If we want to change the momentum of this same object with the same momentum in 2 seconds, the force times 2 seconds equals a delta P of 100, requires a force of 50 newtons. Or C, if we want to use a force of 10 newtons, how long would it take? Force times time equals delta P, change in momentum. 10 newtons, it would require a time of 10 seconds. In our normal experience, the change in an object's momentum is usually due to a change in its velocity. It's usually not going to change the mass. It's generally velocity. It's difficult to change the mass of a spaceship. It's difficult to change the mass of a car. Velocity is easy to change. So force times time, that's impulse, equals the change in momentum, delta P. And we know that P is actually mass times velocity. So delta P is delta mv. And you could write it differently. Mass times final velocity minus mass times initial velocity, which is mass times final velocity minus initial velocity, which this is delta V. So we could say that it is just m delta V. So if the mass remains constant, which is generally the case, delta mv equals m delta V. A net force of 80 newtons is exerted on a loaded wagon of mass 50 kilograms for 4 seconds. Force, mass, and time. Find the wagon's change in momentum. So remember, here is our formula for change in momentum. So the change in momentum equals the net force of 80 newtons times the time, 4 seconds. And this is 320 newtons times seconds. Or in momentum terms, kilograms times meters per second. So if this wagon was initially at rest, how much momentum does it have now? So if it was at rest, initially it had a momentum of 0. So now it has 320 kilograms times meters per second of momentum. These are the momentum units. These units, Newton seconds, are impulse or change momentum. Momentum itself, kilograms times meters per second. Let's say the wagon initially had 200 kilogram meters per second of momentum. Then now it either has, so it had 320, so it had 200 and we added 320. It could have 520 kilograms times meters per second. Or if it originally had 200 kilogram meters per second of momentum and the impulse is in the other direction, it might be 200 minus 320, negative 120 kilograms times meters per second. And this negative value, meaning that our force stopped the wagon and sent it in the opposite direction. So the change in momentum is 320. If you started at 200, you could have ended at 520. or if you started at 200, you could have ended at negative 120. The change in momentum didn't tell us which one it was. But from part C, let's assume that our force on the wagon increased its velocity and that the mass of the wagon did not change. So find the change in the wagon's velocity. So let's rewrite some of the terms from the top. We had a net force of 80 newtons. We had a mass of 50 kilograms, and it was a time of 4.0 seconds. Two methods. Method one, this was before we did Unit 6. Here are some older formulas. Force is mass times acceleration. Acceleration is the change in velocity over time. So we knew the force, it was 80. We knew the mass, it was 50. We could find the acceleration. So the acceleration was 1.6 with units of meters per second squared. If you put it back into this formula for acceleration, 1.6 is the acceleration. We don't know delta V, but we know the time. It was 4 seconds. And so the change in velocity is 6.4 meters per second. The method 2, the Unit 6 way to do this, force times time, is the change in momentum. Change in momentum meaning change in mv. And since the mass of the wagon did not change, m delta v. So all of this, force times time equals mass times the change in velocity. Force is 80. Time is 4 seconds. Mass is 50. And we're looking for delta V. We find that delta V equals 6.4 meters per second, which is the same answer that we got using previous formulas. So we use the idea of impulse in several different familiar situations. For instance, landing when we jump. So when you jump and you land, your knees naturally bend, and that increases the amount of time of your landing, meaning that it decreases the force. If you jump and you land with your knees locked, the time is very small and the force is going to be very big. It could be minimizing the damage in a crash. For instance, your airbag. The purpose of the airbag is to increase the amount of time that you have to slow down. And in fact, cars are designed to crumple in the front in a collision. So rather than just hitting and this hard piece of metal just bouncing, the car is designed and it has crumple zones. And so in the collision, the car crumples and it's slowing itself down as this car crumples and squishes together in the front. Now the crumple zones of a car are basically from the bumper to the back of the engine compartment. So the front part where the engine is. You don't want the cabin to crumple, you want the cabin to be really strong. But the front end crumples pretty well. And the same with the trunk. The trunk is designed in a collision to slow down whatever is hitting the car. So increasing the amount of time decreases the amount of force. The change in the momentum, the impulse, would still be the same. And hammering a nail, another example. So Michael, mass 90 kilograms, jumps so high that his feet are 1 meter off the floor. We're talking about Michael Jordan. Feet are 1 meter off the floor at the apex of his jump. How fast is he falling right before his feet make contact with the floor? So we're going to use the formula v squared equals twice the acceleration times the distance. So here's basically what's happening. He has jumped and he is off of the floor and coming down, and here he is. So this formula will work for ending at rest as well as starting at rest. So v squared equals twice the acceleration times the distance. So the acceleration is gravity, 10 meters per second squared, and it is a distance of 1 meter. And so the velocity is the square root of 20 meters squared per second squared, which is 4.472 meters per second. So this is how fast he is moving right before his feet make contact with the floor. How much momentum will Michael have just before he lands? And remember, momentum is P, it's mass times velocity. So Michael's mass is 90 kilograms, and we found his velocity right before he lands, 4.472 meters per second. And so his momentum is 402 kilograms times meters per second, and this is an instant just before he lands. Michael's change in momentum will be 402 kilograms times meters per second as he comes to a rest. Find the landing force acting on his legs in a couple different conditions. One, if he bends his knees as he lands, coming to rest in 0.5 seconds. So force times time equals change in momentum. Impulse equals change in momentum. What is the force if this happens over 0.5 seconds? Delta P was 402. The force in this situation is 804 newtons. It's a pretty significant force. What about in situation B, if he keeps his knees stiff as he lands, coming to rest in 0.1 seconds? Force times time, that's impulse. Change in momentum. Force. Time is 0.1 seconds. And the change in momentum is still 402. And the force here ends up being 4,020 newtons. When we jump into the air and land, our change in momentum is going to be the same whether we bend our knees or not. We bend our knees when landing in order to stretch the time of the impact, thus lessening the force of the impact on our knees, ankles, and legs. And actually, you can put your back in that list as well. A lot of times landings will really shock your back. If you have the misfortune to leave the roadway and head for a ditch, you should head for the bushes and away from the trees or the concrete pillars. Whichever you hit, your change in momentum will be the same. From some value, hopefully not too much, and down to a value of 0. If you hit the tree, your time of impact will be shorter or longer? Shorter. Which means the force of the impact will be greater or less? Greater. If you hit the bushes, the time of impact will be lengthened, which will make the force of the impact smaller. The yellow plastic barrels, which surround the concrete pillars at some overpasses, are meant to lengthen the time of impact. Same idea with guardrails. Guardrails have shear bolts on them, and if you hit the guardrail, it's designed to crumple a little bit to increase the time, which decreases the force. So if you consider that in either instance, this is your change in momentum, you can have a big force over a small amount of time, or you can have a small force over a longer period of time. When one goes up, the other one goes down. When one gets bigger, the other one gets smaller. In terms of hammers, you want to choose a hammerhead made of steel, not rubber. The hammerhead strikes the nail with a certain amount of force, and the momentum will eventually become 0. If we shorten the length of impact by choosing a steel hammerhead, the force of impact with the nail will be greater. So you're looking at a shorter period of time and a larger force driving the